everyone, and welcome back to this series on differential equations. Today we're going to be continuing our exploration of differential equations in the general sense, and also add a couple new numerical methods to our toolbox. Up to this point, you should be able to solve any higher order ordinary differential equations up to some degree of difficulty, and also maybe even know how to solve systems of differential equations. We already have the Forward Euler, which sometimes is just called the Euler method, for solving differential equations, but it's typically only used for first order and can be applied to higher order if you know how to convert it to a first order system. So what I want to do today is introduce two other methods known as the Backward-Euler and the Crank-Nicolson method for solving differential equations, and then you can use all three methods to sort of generate numerical solutions and compare your results. The Backward-Euler and the Crank-Nicolson method don't have superior results in the ordinary differential equation domain, but definitely once we start talking about partial differential equations, the Backward-Euler and the Crank-Nicolson method do have their spotlight there. But I think it's a little bit more useful to sort of get used to the Backward-Euler and Crank-Nicolson method in the basic ordinary differential equations case before we actually enter the realm of PDEs, where things can become quite complicated very quickly. So let's first off start off talking about the Euler method or the Forward Euler method and sort of where it comes from. And with that idea, we can actually build the Backward Euler method very easily. And we'll also talk about why we call it the Forward and Backward Euler method as well. So our goal, generally speaking for the first order case, is to solve the differential equation y prime of x is equal to fxy with the initial condition that y of x is 0 is equal to y0. And for the sake of simplicity, let's assume that this solution does exist and is unique. So the Forward Euler method, so the Forward, or aka just the Euler method, for solving this differential equation, you probably already know. And it comes of the form y of x plus h is approximately equal to y of x plus h times fxy. Right? And the important thing that I want you to realize is that this object is what we want in this particular calculation. And on the right-hand side, this is what we know. So what we want and what we know on the left and right methods. So what we want can be easily isolated on the left. So from this is what I'm going to refer to as an explicit numerical method. Explicit numerical method, because we don't necessarily need to solve anything algebraic in order to get what we want directly. So one theoretical question you may ask for this particular equation, y of x plus h is equal to y of x plus h times fxy, is where does this come from? You can actually derive the Forward Euler method from a variety of ways, Taylor series being one of the most popular ones, but I want to view this from the integral perspective. So again, if we have y prime of x is equal to fxy, if you remember how we sort of solved this from the Pickard iteration scheme, what we can actually do is integrate both sides of this equation. So we can represent this as the integral from x to some point in the future, let's call it x plus h, of y prime of, let's say, t dt, so t is just a dummy variable here, and that would be equal to the integral from x to x plus h of f of t, y of t, dt. Right? So the left-hand side is just going to be a fundamental calculus evaluation. So on the left-hand side, we're going to have y of x plus h minus y of x, so you can automatically see where the Euler method is going to come from. But the right side, is slightly more complicated, so we're just going to leave that as it is. So x times x plus h times f of t, y of t, dt. Okay, so let's analyze this right-hand side from the numerical perspective and see if we can get anything out. So if we look at things on the t perspective, and let's assume that t ranges from x to x plus h, and let's look at this function f, which is generally speaking a function of t only, but if we know y is a function of t, so technically this only has t in it. So if we look at this curve, let's assume that this is our function f, if our h is small enough, so if our h is practically 0, then what we see here is that this curve is practically a flat line. So almost a flat line. Almost a flat line as h is approximately equal to or approaches 0, right? So that means it's either going to be equal to f of x, or it's going to be equal to its other height value, which is going to be f of x plus h, right? So keep in mind, f of x and f of x plus h will be equal to the same exact thing if that line is indeed constant, but theoretically they are different if your h is non-zero. So the forward Euler method, evaluates at t is equal to x, right? So if we evaluated at t is equal to x, then that integral will simplify. So we're going to have y of x plus h will be equal to y of x plus, and that integral becomes a constant. So we evaluated f of x, or at x instead of at t is equal to x, so we're going to have the integral from x to x plus h. So everywhere we see t, we replace it with x, so we're going to have f of x, y of x times dt, because this is the integral with respect to t, not x, so we can actually factor that out. So once we have that, we're going to have y of x plus h is equal to y of x, and then we're just going to have an integral with respect to t, which is just going to be t, evaluated x plus h minus x, which is just going to be equal to h. So we're going to have h times f of x, y of x. And that is our familiar Euler method. So what is the difference between the forward Euler method and the backward Euler method? So the backward Euler method, which I'm just going to eventually represent as just BE versus FE, is it evaluates, you can take a guess, so it evaluates at t is equal to x plus h instead of t is equal to x, like the forward method does. So once we do that, we're going to have y of x plus h will be equal to y of x plus h times f of x plus h, y of x plus h. And this would be the backward Euler method. Now, what's interesting about the backward Euler method, again, y of x plus h is what we know, but it's also located on the right-hand side. So that's what we want to know, which means we have to solve for it, right? So it's not a direct method. This is usually what we refer to as an implicit method. And usually you would have to use numerical methods such as Newton's iteration method or Banach's fixed point iteration method or other algebraic solvers in order to figure out that numerically, and you have to do that on every single time step, right? Or every single h step, I guess you could say. So that's what the backward Euler method is versus the forward Euler method. Let's actually take a look at a numerical example to sort of see how we would implement these. Let's look at this particular initial value problem. Y prime is equal to 500y. This is a very easy differential equation to solve because we can just be like, oh, we can use, for example, separability of this differential equation and find that the actual solution should be y is equal to 3 times e to the power of 500x. Now you might be wondering, why am I choosing such a large number for that coefficient? So what you actually see here, if you graph the solution, is because this actually looks practically like this. This is very, very steep. Usually when we have differential equations whose solutions are very steep, we usually call this particular ODE a stiff ordinary differential equation, or some people will also call it a steep differential equation. And usually some numerical methods will usually fall in these particular cases, which might motivate you to use other numerical methods as well. So let's actually look at a forward Euler scheme on this particular solution and see what happens with it. So let's use a forward Euler approximation. So what is forward Euler? So forward Euler will be doing yk plus 1 will be equal to yk plus h times f of xk yk. And keep in mind, our fxy will be equal to, it will be equal to 500y. So if we just replace that in our particular case, that's going to give us yk plus 1 will be equal to yk plus h times 500 yk. We can easily solve for yk to create an iteration scheme, so we're going to have yk times 1 plus 500 times h. Right. So that's going to be our iteration method, so we can easily generate. So let's assume that we use an h equal to, I don't know, let's use h is equal to 0.01. So if we do that, our first numerical method, which is going to be located at 0.01, will be equal to approximately, what would that be? So it's going to be equal to y0 times 1 plus 500 times 0.01. And keep in mind y0 was chosen to be equal to 3, so it's 3 times that particular object, and once you actually do out that math, you're going to get 18. If you do y2, that's going to be equal to y1 times 1 plus this 500 times 0.01, and that's going to be approximately equal to 108. So if you look at these particular two solutions, where this is located at 0.01 and this is located at t is equal to 0.02, we can actually look at the exact solution because we actually know what it is equal to. So true solution is going to be equal to what? So one can find that this is actually supposed to be 445.2 and 66,079.4 approximately. So what's the difference between those solutions? A lot, right? So that's actually a really bad numerical method. Actually, in fact, this Forward Euler method is very bad if your h chosen is greater than or equal to 0.004. And I'll let you sort of explore on your own why that is the case. That goes into a long discussion about numerical stability of numerical schemes, which we'll definitely focus on a little bit more later. But keep in mind, if you choose a large h, larger than some special number, the method usually is going to give really off results, as we can clearly see here with this particular example. So even if you didn't know the exact solution, 3 times e to the 500x, you should know that the solution should be growing a lot faster than 18 to 108 in a time step of 0.01, right? So you're like, okay, I might not know what this exact solution is, but I know my numerical method is not going to converge fairly quickly to it. So that's where you might be motivated to try other numerical methods. So let's see if our Backward-Euler method gives us anything better. So our Backward-Euler method, the general scheme would be equal to what? So again, we're going to have yk plus 1 will be equal to yk plus h times, and this is where it's slightly different because it looks at a point in the future, not the present. So it's going to be equal to xk plus 1, and then yk plus 1. Right? And again, as usual, it's an implicit method because yk plus 1 is located on both sides of this equation, so we would have to solve this, hopefully analytically, in order to get a nice method out. So for our general case, what would y1 be? So y1 would be equal to y0 plus h times f of x1 y1. And using our particular example, that's going to be y1 will be equal to y0 plus h times 500 of y1. So let's actually solve this equation for y1 because it's actually pretty easy to solve in this particular case. So once we isolate things, in particular we move that particular character over, we're going to get what? So we're going to have y0 plus 500h minus 1 times y1 will be equal to 0. So we can isolate this for y1. So y1 will be equal to our, what would that be? Let's do y0 positive all over 1 minus 500h. All right, let's write that as our y1. And generally speaking, we're going to have yk plus 1 will be equal to yk all over 1 minus 500h. right? So once we have that, then we have this particular numerical method. Now notice it's possible for this to be negative, and just by understanding our particular differential equation, we should have exponential growth. So we should not have any decreases or negatives in our value since our initial condition starts as positive. So what we want is we want to choose an h such that 1 minus 500h will be a positive number. Right? So how am I going to do that? So that's going to be equal to minus 500h must be greater than negative 1, which means 500h must be less than 1, which means h must be less than 1 divided by 500, aka 0.002. Right? So this is going to avoid oscillatory steps. Right? So that's pretty much what we have here. So if we choose that h, that doesn't necessarily guarantee stability, but it does guarantee at least something reasonable. So with that in mind, let us choose our h to be equal to 0.001, which indeed satisfies that oscillatory avoidance, right? So also keep in mind, this means that the Forward Euler method will be happy associated to that claim that I made previously. Right? So let's choose that h for both the Forward Euler and Backward Euler, and then compare that to the exact results. So let's look at our t for 0. Keep in mind that's our initial condition. Our Forward Euler scheme will obviously produce 3, since that's the initial condition. Our Backward Euler will also produce 3, which is the initial condition, and the exact, obviously, should be equal to 3 as well. So once we look at our h points, which will be 0.001, 0.002, and 0.003, let's go 3 steps up, and then plug them into our iteration methods and compare. Let's see what we get. And maybe you want to make a little prediction before I actually show you the results. So for Forward Euler, you will get 4.5, 6.75, and 10.125. My exact solution will be 4.95 approximately, 8.15 approximately, and 13.45 approximately. So you can actually look at my Forward Euler calculations, and they're actually not too bad because our h actually satisfies something nice. So will Forward Euler or Backward Euler be more appropriate for this particular setup? Well, you can try it and plug in. What you're actually going to get is you're going to get 6 for that, 12 for that, and 24 for that. So you actually see that the Backward Euler actually performs slightly worse than the Forward Euler method and actually overshoots our solution by quite a substantial margin, right? But on average, you know, it overshoots it, Forward Euler undershoots it, you know, not everything is perfect. That's why you always look at several numerical methods and compare the results to see sort of, you know, what is best for your particular differential equation. Now, one thing that you may observe for this particular example is that the Forward Euler approximation is actually less than the exact solution, and that's less than or equal to the Backward Euler method, which appears to be an over approximation. So one may ask the question, what about the average of these methods? And that's where the Crank-Nicolson method comes into the picture. So let's briefly introduce the Crank-Nicolson method. So the Crank-Nicolson method. Some people also call this the midpoint or the trapezoidal rule. So the midpoint or the Crank-Nicolson method can be viewed as an average of the Forward Euler and the Backward Euler schemes. And the general form follows as so. So yk plus 1 will be equal to yk plus h over 2 times the average of fxk yk and fxk plus 1 yk plus 1. So there's your Forward Euler, there is your Backward Euler term, and the over 2 corresponds to the average of those two objects. Right? So if you want to sort of explore for our particular example, how would you do that? So generally speaking, for our case, we have yk plus 1, which will be equal to yk plus h divided by 2. And then we're going to have 500 yk plus 500 yk plus 1. And then we can isolate this equation for yk plus 1 and then iterate from our initial condition. So once we do that, what are we going to have? So we can distribute our 1/2 and our hn, and that's going to give us a couple 250s. So we're going to have yk plus 1, which is equal to yk plus 250 hyk plus 250 hyk plus 1. And then we can start isolating all of our terms together. In particular, we can subtract this yk plus 1 term, off, and then see what we get. So when we get that, what do we have? So we're going to have yk plus 250 hyk, and then we're going to have, now keep in mind, that's not 250 minus 1, it's 250h minus 1. Don't forget that little h that's sort of hanging out there. So we're going to have our, what is this? Let's make sure. So it's going to be 250h yk, and then we can write this as 250h minus 1 yk plus 1 will be equal to 0. All right. So once we have that, then we can sort of isolate everything around, and we're going to have yk plus 1 will be equal to, subtract that. They're both going to be negative, then we're just going to reverse that anyway, and that's going to be yk 1 plus 250, and that's going to be h. Let's not forget our lonely little h term, so 150h, all over, and then we're going to have 1 minus 250h there as well, right? So that's going to be our Crank-Nicolson iteration method for our particular example, and obviously you want this 1 minus 250h to be positive, so you avoid any oscillatory behavior. So for example, as long as your h is less than 1 over 250, then you should be good to go. And I invite you to sort of use this iteration method and compare your results against Forward Euler and Backward Euler and see how close they are to the exact solution. For the next example, let's actually look at a second order differential equation and see how we can use Forward Euler, Backward Euler, and Crank-Nicolson method to solve these numerically as well. The reason I choose such a basic ODE now, y double prime plus 5y prime plus 6y equals 0, a nice constant coefficient, second order, homogeneous differential equation with some initial conditions, is because we can easily find the exact solution to compare our numerical solutions to. In particular, you should be able to find that the exact solution for this differential equation, using whatever methods you want, is 3e to the minus 2x minus 2e to the minus 3x. So from this you can generate the exact solutions and then compare. You also might want to calculate its derivative, y prime, to be equal to minus 6e to the minus 2x plus 6e to the minus 3x as well, because you're actually going to be calculating approximations for the first derivative as well when you work through this example. So, in case you don't remember, any higher order differential equation can be represented as a system of first order differential equations of other variables. Keep in mind, since we're working with a second order differential equation, we need to introduce two new variables. Let's call those variables eta1 and eta2. Eta1 will be defined to be equal to y, and eta2 y prime. Once we define these two new variables, we're going to have eta1 prime and eta2 prime, which is going to give us y prime and y double prime. But again, keep in mind y prime has a new name. Its new name is eta2. And y double prime can be isolated in our original equation to be equal to minus 6y minus 5y prime, aka minus 6 eta1 minus 5 eta2. Once you have that, then you have your first order system, for which we can write as follows in more of a simplistic manner. Eta1, eta2 prime will be equal to eta2 of x. Let's also write our x on the left-hand side since they're functions of x only. So that's a function of x, and that's going to be equal to eta2 of x, and this will be equal to minus 6 eta1 of x minus 5 eta2 of x. This is going to be the basis for our numerical approximations, and keep in mind our initial conditions are going to be eta1 of 0 is equal to 1, and eta2 of 0 is equal to 0. Remember, eta1 is y in disguise, and eta2 is y prime in disguise. So what would our Forward Euler method look like? So we're going to approximate eta 1 prime and eta 2 prime with forward Euler methods. So once we do that, what are we going to have? So that's going to be eta 1 x plus h will be equal to eta 1 of x plus h times eta 2 of x, right? And then eta 2 of x plus h will be equal to eta 2 of x plus h times, and since I have two negative signs, I'm just going to factor out my minus sign just to make it a little bit more nicer to look at. So we're going to have eta 1 of x plus, and let's not forget our lonely little coefficients either. So we're going to have 6 eta 1 of x plus 5 eta 2 of x. Right? So that's our forward Euler method. And what would our backward Euler method look like? So our backward Euler method would look like eta 1 of x plus h will be equal to eta 1 of x plus h times eta 2 of x plus h. And then eta 2 of x plus h will be equal to eta 2 of x. And then let's do the same exact setup here. So let's do minus h. So minus h. And then we're going to have 6 eta 1 at x plus h plus 5 eta 2 of x plus h. Right? Now our forward Euler method is actually all ready to go for iterations, but our backwards Euler method needs to be slightly rearranged. But this is a little bit more difficult because notice that this is what we don't know, but it's located in another formula, right? So we have an unknown on an equation with another unknown as well, in particular two unknowns, eta 1 and eta 2, both evaluated at x plus h. So let's actually rearrange this and see if we can build maybe a system out of it. So if we do that, we're going to have eta 1 of x plus h minus h times eta 2 of x plus h. And eta 1x we know, so I'm just actually going to leave that on the right-hand side. And on the left-hand side, we're going to have what? So we have minus 6h on the right, so that's going to be positive 6h. On the left-hand side, that's going to be eta 1 x plus h. And then we're going to have our eta 2 terms. So we're going to have eta 2 x plus h, and then minus 5 turns into positive 5h. And then we're going to have our eta 2 x plus h, and that's going to be equal to eta 2x. So once we have this, then we can sort of analyze what we have here. Notice that those are technically common terms grouped together. That's my eta 2 term, that's my eta 1 term, that's my eta 1 term. So my unknowns are eta 1, eta 2 at x plus h. So I can write this in a more compact form using the coefficients which depend on h only. So we're going to have 1 minus h, 6h, then 5h plus 1. So that's a 2 by 2 matrix, multiplied by the vector eta 1 x plus h, eta 2 x plus h, and that must be equal to eta 1x, eta 2x. Right? So we have this object, which is going to be our coefficient matrix. It's called A, which technically depends on h only. Then we have our eta prime is equal to eta. Right? So all we need to do is just solve this equation for eta prime, and then we're done. And keep in mind this has a unique solution as long as the determinant of AH is not equal to 0. And the determinant of AH will be equal to 5h plus 1 minus positive 6h squared. So as long as h does not equal, what is that, minus 1/2 and minus 1/3, then we should be okay. And usually we don't use negative h's anyway, because technically we're moving in the wrong direction if our h is going backwards, right? So since h is usually positive and a positive small, then we should be good for any h you choose, at least in the theoretical realm. So that's how you would start to set up your backward Euler method. So now let's start to generate our numerical solutions with these iterations that we have already built. Right? So let's assume that h is chosen to be 0.1, and we're going to do this for the forward Euler and backward Euler schemes. So what are we going to have? So we're going to have eta 1 at 0.01 will be equal to 1, the initial condition of eta 1, plus our h times the value of eta 2 at our initial condition, which is going to be 0, which is trivially going to be equal to 1. And then we're going to have eta 2 evaluated as 0.01, which will be equal to the initial value of eta 2, which would be 0, and then minus that 0.01, and then we're going to have our 6 times 1 plus 5 times 0, which is going to be approximately, what is that going to be? That's going to be negative 0.06. Right? So that's going to be our first point. Let's do a couple more points as well. So eta 1 at 0.02, so we're going to use those values that we just calculated. So eta 1 evaluated at the last point, which is going to be our 1, plus our h value, 0.01, times the old last value of eta 2, which is going to be negative 0.06, and then eta 2 at 0.02 will be equal to the last value of eta 2, which is negative 0.06, minus our h value times our next iteration, which would be 6 times 1 plus 5 times negative 0.06. And then once we find out those values, what will that be? That's going to be approximately 0.9994. And this is going to come out to approximately negative 0.117. Right? And the next value, let's do eta 1 of 0.03 and eta 2, which is 0.03 as well. So eta 1 of 0.03 will be approximately equal to 0.9994 plus 0.01 of negative 0.117. And the last value we actually don't need unless you want to go up to 0.04. So I'll leave that value there. And this value for eta 1 of 0.03 will be approximately 0.99823. Right? So that's going to be our first 3 numerical approximations. Now let's go ahead and do our, keep in mind that's for Forward Euler. Now let's do the same for our Backward Euler, which turned into a linear system for this particular problem. So let's take a look at that. So this is going to be our Backward Euler scheme. So at the present time, we have our AH matrix times our eta x plus h vector, and that's going to be equal to our eta x vector. So keep in mind, this is going to be invertible for any positive h, so we can just multiply both sides by that. So that means eta of x plus h will just be equal to the inverse of that matrix, h, times eta of x. And then we can multiply that matrix times that vector for all of our initial old values of eta, and then we can just iterate that quite easily in whatever language, or you can do that by hand since it's a 2 by 2 times a 2 by 1. So using that, you're going to have that eta 1 at 0.01 and eta 2 at 0.01. That vector will be approximately equal to 0.9994 and negative 0.0571. And I definitely invite you to try this implementation on your own. And then eta 1 at 0.02, and then eta 2 of 0.02. So you're just going to take that AH inverse matrix and multiply by that vector that we just got. And then you're just going to have approximately positive 0.9983 and negative 0.1114. And let's do it one more time so we can have the same number of points. So we're going to have eta 1 of 0.03 and eta 2 of 0.03. And that's going to be approximately equal to 0.9967, and that would be negative 0.1631. But keep in mind, technically, we do not need that value unless we want to do one more iteration. So now that we have these results at 0.01, 2, and 3, let's just combine all of our results into a nice little summary table to sort of see who did better on this round. So once we build our table, let's make this really nice, and let's not put 0 on the first row since we already know that that's going to have a 0 error. So we're going to have 0.01, 0.02, and 0.03 as our points of focus, and we can go further if you have it already implemented in some coding language of your choice. So we're going to have our Forward Euler method. Let's actually look at the value and the error with respect to the true solution, which we've already generated. Let's also look at the Backward Euler scheme. So the Backward Euler scheme, let's erase that if it wants to erase, maybe it doesn't. So our Backward Euler scheme, let's look at the value and the error associated to that term. And then, once we have that, then we can analyze the error for each of those terms. And let's see if that wants to erase or stay that color pink. It's up to it, right? So let's look at the true value over here. Right? So let's see what we have in this particular table, and let's see who did better. So we're going to have 1 here. We're going to have 0.9994 there, and then we're going to have 0.99823 as its value there. We're going to have 0.9994 for backward Euler, and then 0.9983, and then 0.9967. So keep in mind I'm only focusing on eta 1 here, so I'm only focused on y. And then the true value one can find using that exact solution actually is 0.9997, 0.9988, and 0.9974. So now let us look at the error, and in particular I'm going to be looking at the absolute error for both of those terms. So the absolute error for that is going to be equal to 0.0003, so we would like this to be as close to 0 as possible, 0.006, and then 0.0008 for our forward Euler method. Over here we're going to have 0.0006, which is slightly bigger than our forward Euler method, but then we're going to switch into 0.005, which is smaller, and then 0.0007 for that last. So in conclusion, you can say that the backward Euler is a little bit better for this particular equation, right? So, of course, I'd leave to you as an exercise to sort of compare what the Crank-Nicolson scheme is actually going to do and see what its accuracy is with respect to the true solution. And just a heads up, you will also be using a linear system solver in order to solve that particular problem as well, because it does have that implicitness associated to the backward Euler method in that equation scheme. So this is just an introduction to Crank-Nicolson, backwards Euler, and forwards Euler for both differential equations and differential systems. Hope you enjoyed this video, and I'll see you in the next one. Take care.